There are a lot of electric heaters installed and put in processes all over the world, and not one of those heaters runs without a temperature controller, a sensor, a relay, or some sort of a thermal device. 4 devices combine together to make what we call the thermal loop. The thermal loop consists of the control, the relay, the heat source, and the sensor. It's really common for people that are tasked with designing electric heating systems to not focus on the temperature control. Most of the people tasked with designing electric heating systems are dealing with a mechanical product in nature. It bears pressure, it creates temperature, it's got flow to it, and so those things are all looked at very carefully. But those things don't really work very well if you don't have the proper control in it. So a lot of time and consideration needs to be put into the temperature control mode for that application. There are 3 main types of temperature control that can be used in any heating system. There's on-off control, there's proportional control, and there's PID control. The thermal loop is a system of components that all work together to keep your process at a steady temperature. The primary device in this system is the temperature controller. The temperature controller receives input from a sensor that's actually installed in your process. You have a temperature that you want to maintain, whether it's freeze protection or 1,000,000 degrees, and that sensor has to be able to accurately tell the controller what the actual process temperature is. That's called a process variable. That controller then makes a decision to send a signal to some sort of a relay that allows voltage or power to be applied to the heater itself. When the heater turns on, it applies heat at a rate that will eventually satisfy that sensor, and then the sensor sees that it's above the temperature and it shuts the system off. A controller in the thermal loop is designed to maintain a specific temperature over a specific period of time. The reliability and capabilities of each type of controller varies greatly. So with on-off control, for example, a less precise application, a proportional control application may be something that needs to be a little more precise, and a PID loop in a temperature control in the thermal loop is extremely precise. We're going to talk about each one of these methods today. On-off temperature controllers are the most common type of temperature controller out there. Good and reliable, rugged. As a matter of fact, this sensor is the one we use in every single ready-to-ship Powerblanket that goes out the door here at Powerblanket. These controllers are made up of a device inside that can sense temperature, and then it can open and close a relay to allow power to flow to a heater or to turn a heater off and on. These controllers are very reliable. You can think about maybe the last time you ever replaced a sensor in your oven at home. On-off temperature controllers also come in this format. This is an on-off temperature controller very commonly used to switch single-phase power loads in heat trace or small heaters, and they come with a bulb and capillary sensor, and the sensor is attached into the controller to a thermostat that's built inside of the unit, and that thermostat has a relay that again allows the power to be gated to the heater to turn it on and off based on the temperature that's set in this controller. Proportional controllers are another type of temperature control. A proportional controller like this Powerblanket GHT controller is used to control a process at a little tighter temperature than with an on-off controller. These units have a sensor that's attached to the process, power coming into the process, and a way to hook up to the process to run the heater. These units have a relay inside of them. They have a microprocessor that can basically make decisions based on temperature and when they turn on and when they turn off. And they provide a lot tighter control, plus or minus 5 degrees around the set point. A PID controller is the most accurate form of control. This is a really simple example of a PID controller. Here we have an 8th DIN red line controller that has a thermocouple input and has a way for power to be applied to the unit and a way for power to go to the load. Again, just a really simple example. What's happening here inside this controller is it's receiving an input from this thermocouple at a sampling rate of multiple times per second. This controller can then take that temperature sensing reading from this thermocouple or RTD and make adjustments to the output to the heater over a very short period of time. PID controllers literally have no overshoot. They can get right to the temperature and hold it dead on. So if you're heating a great big huge tank of tar, you don't need a PID controller. A proportional or on-off controller would work just fine for you. But if you're trying to keep a gas stream at a very precise temperature, or if you have vapors or solids that will settle out below a certain temperature, this controller is the best controller for that application. Very precise and very accurate. The thermal loop also includes a system called a relay. The temperature controller sends a signal to the relay. There's really three main types of relays used to switch power to an electric heater. They act as a gate for the voltage to go to the heater so that it can create the heat. One type is what's called a mechanical relay. These are often called motor starters or just plain relays. They tend to be mechanical devices that switch on and off. Then there's a solid state relay, which switches on and off at a higher frequency and can last a lot longer, can have up to 1,000,000 cycles. And then finally, there's the SCR, a silicon controlled rectifier. SCRs are the finest type of relay that are given a signal from a temperature controller to control a load and are capable of making changes on-off multiple times in 1 second. Mechanical relays are a relay that make and break voltage to a heater. In other words, they get a signal from the controller and then the coil is pulled in and the mechanical relay makes contact and allows the voltage to flow through the heater and back to the circuit. So just like a valve, or just like a lot of times people compare electricity to water, it opens and closes that gate to allow voltage to come on and come off. These relays have been around for a long time and they work great for low accuracy, high volume type applications, but they do wear out. They're limited to about 100,000 cycles. The most common types of mechanical relays are what's called like a motor starter or a mercury displacement relay. These relays, again, have parts that wear and can wear out over time, and they're not quite as accurate, so they're mostly paired with an on-off controller. A great example of how a mechanical relay works with an on-off controller running it would be if you pulled up to a stop sign in your car and the speed limit was 50 miles an hour after the stop sign. When it was clear, you put your foot all the way to the floor, 100% power for your car, up to 50 miles an hour, and as soon as you hit 50 miles an hour, you take your foot all the way off the gas. You don't hit the brake, but you take your foot off the gas. And then when you go below 50 miles an hour, you put your foot all the way to the floor again. That's how a mechanical relay works in conjunction with an on-off controller. A solid-state relay is another way to switch power to an electric heater. Solid-state relays use diodes, which you could also call gates, and they can turn off and on as fast as 1 time per second. So it's a much finer form of control. So for a controller, you would need something like a proportional controller or a PID controller that's capable of sending signals that fast and listening to the sensor in the application and sending a demand to this relay. So these relays can turn off and on a lot faster. They provide a lot more accurate control and a much more dependable flow of electricity and use of electricity into an application. The temperature swings aren't as high when you use that type of a relay because they're being turned on and off every second at the minimum. An SCR power controller is another form of relay that you can use to transfer power after a signal is given to a relay to your heater in your process. An SCR power controller utilizes diodes that can turn off and on 120 times per second. Every single cycle crosses zero from AC to DC. There's 60 of those in 1 second. An SCR power controller is capable of turning off and on 120 times per second. So if you have a controller that's capable of sensing your process and asking for changes multiple times in 1 second, an SCR can handle the job because it can change the output to the heater rapidly and accurately. So if you need precise temperature control or a more efficient use of your electric power, an SCR power controller is a very easy upgrade in a system that needs to be accurate. Temperature sensors are the most vital part of the entire thermal loop. If you have a temperature controller that doesn't have a good sensor, you don't know what your process is doing, and your heater doesn't know when to turn a relay on or off. We talked about a simple thermostat, which we use here at Powerblanket in a lot of our systems. Again, the most widely used temperature sensing device in the world. It's placed right on the surface of the process. This one happens to combine 2 technologies in one, in that it has a relay in it. But the idea is that it senses the temperature right where the temperature needs to be sensed. A second example is a thermocouple. Thermocouples consist of 2 dissimilar wires. This is a type J thermocouple. There's a lot of different types of thermocouples, but this is the most common one. A J thermocouple consists of an iron wire and a Constantine wire that are joined together with a little braze. At different temperatures, it puts out a different EMF, and your controller can sense that EMF. It's a very light voltage signal, and make corrections to the output to the relay and to the heater. So when using a thermocouple, you got a pretty accurate form of control. Another type of sensor that's really common is an RTD. These are a couple different common RTDs. RTDs are what's called a resistance temperature detector. RTDs will actually put out more resistance at higher temperatures and lower resistance at lower temperatures. These RTDs are very accurate and can be placed in a lot of different locations. What's most important is where is that temperature sensing point most important for you. If sensors are the most important part of the thermal loop, where you put them is actually even more important. Sensor placement means that I put this sensor in the exact area where the heat needs to be added. So if you have a surface that needs to be controlled at a given temperature, you need to make sure that sensor is right on that surface. This is an ambient air sensing thermostat that's designed to be put into standard hardware. It senses air temperature outside. So in a typical heat trace application or a freeze protection application, when it sees, say, a temperature of 35 degrees, it turns the entire heating system on. So this needs to be placed up in the air, maybe on the north side of the plant in the wind in the coldest possible part of the plant, not hidden behind an I-beam or down in a warm area inside of a building. A sensor could also be placed on a pipe. It could be placed inside of a tank, but make sure that it's in the application right where it needs to be so your heater can provide the most efficient form of control based on the type of controller and the type of relay that you've selected. Powerblanket offers complete thermal solutions, whether it's the temperature sensor, the controller, the relay, or the heater. We can do a large variety of applications. We've got a lot of people here that have a lot of experience helping people like you in your facility. No matter what the application is, Powerblanket has you covered.